Hello everyone. In our last lab, we determined a Newton's second law for rotation, in which we found that the net torque is equal to the rotational inertia times the angular acceleration. This is an alpha, right? What we're going to do over the next few days in a couple of different labs here is figure out all about this rotational inertia thing. It functions much like mass did in net force equals mass times acceleration. Right? It functions as what we're calling the rotational inertia, a capital I, what some profs might call a moment of inertia. So if you see that on an AP test, moment of inertia means our rotational inertia. Okay? So we define the rotational inertia graphically to be the slope of a graph of torque versus angular acceleration, right? Which is still a way we could find it now. Okay? But we also defined it as being, as any inertia, right? It's the tendency of an object to continue in its same state of motion. In this case, its same state of rotation. And if it's not rotating, it tends to keep not rotating. If it is rotating, it has objects have a tendency to keep rotating with the same angular velocity. It's a measure of an object's resistance to changes in its rotation. How hard is it to get it to angularly accelerate, right? Since angular acceleration is the rate of change of angular velocity. Or if you wish, it's how hard it is to start it or stop it, right? Get it started or stopped. The same way that mass functions linearly, right? Rotational inertia functions this way rotationally. Now, question is though, how do we figure out how much rotational inertia a rotating object has? This is the part which is simple to do linearly when it's just mass, but will be quite a bit more complex when we're dealing with rotation. Consider these blue and red inertia wands, all right, that I'm going to hand out to you so that you can see them and play with them a bit here. And if not, if you're watching this from home, you may want to get a hold of these or look at them. But these inertia wands basically have the same mass, okay? You can shake them straight up and down. Don't rotate them at all yet. Straight up and down to kind of get a feel for how much mass they have, how much inertia they have. Resistance changes their motion. Right? You can also just throw them on a scale. They're within a gram or two of one another, so they're almost identical masses. However, twist them. Right? Twist them, rotate them, right? While holding them in the middle, right? Like in the picture, kind of twist them side to side. I think you will notice a huge difference between them when you try to twist them. Right? The blue wand is much harder to twist. Much harder to twist than the red one. Even though it's got the exact same mass, or very close to the exact same mass. So of course the question then becomes, why? Why does the blue wand have more rotational inertia than the red wand, even though they have the same mass? Well, the key is if you look at the little holes, right, that are on those wands, look where the masses are. On the blue wand, the masses are at the edges. They're at the very end. There's little holes up here that you can see them. And then there's little holes in here that you can see that there's nothing there, right? It's clear all the way through. But the red wand, the masses are right in the center or near the center. Right? And there's nothing way out here on the edges. So it appears that rotational inertia doesn't just depend on how much mass something has, but also where that mass is located. Much like when we did the difference between, say, force and torque, right? Torque depended on not just how much force, but also where that force was applied. Well, rotational inertia will depend not only on mass, but how that mass is organized, where that mass is, right? And what its orientation is and its configuration is about the axis of rotation. Right? And if you notice here, the units that we found for rotational inertia were kilogram meters squared. Right? This was the, remember to linearize the graph, we had torque. I'm sorry, we didn't have to linearize that graph. Torque over angular acceleration, and when we reduced the units, right, we got kilogram meters squared, which is mass and distance. distance squared, but still distance units. So it looks like the units kind of were a hint that it wasn't just about how much mass, but also where that mass is from the axis of rotation. So that leads us to the purpose of today's lab, to create graphical and mathematical representations of the relationship between the rotational inertia, capital I, the total mass, which we're going to call m, and the distance the masses are from the axis of rotation, which we're going to call r, like we did with torque, for a system of particles consisting of 2 point masses. Right, so we're going to start out by looking for the rotational inertia of 2 point masses. Okay, masses that we can consider to be just kind of one little point. We'll get to more complex objects as we go through this. Okay, a lot more we have to do to get there, though. Now, note that this is a 3-variable lab, right? And as such, we are going to have to do at least 2 parts because, you can only change one variable at a time, hold the other one constant. Now, we actually have to do an extra part in this, but I'll explain that in a little bit because of the equipment we have. So the question is then, how are we going to find all of these things? Okay, well, we're going to use the same apparatus that we've been using in the last few labs, right, which allow us to measure the angular velocity as a function of time, right, with the rotary motion sensor. And we have these masses here on the rod, which can be moved in, right, and out to change the distance. And we can actually add masses. We have a little different screw than it shows in the picture. We have a big screw. We can actually add masses to these, right, to change the total mass of our point masses. So note, we can control both of those things. Now, one thing about that, and you'll probably hear me say this a couple times, but we need to keep this thing vertically balanced. Okay? If we pile a bunch of masses only on one of these, or we only move one of these, right, in or out, that's going to create a torque, a net torque on this, right, up and down, and the device doesn't like that. All right? So if you add a mass to this one, you got to add a mass to that one, same mass. If you move this one in or out, you have to move this one in or out the same amount. That's the only way we're going to, not hurt the device, please. So don't screw around with it, right? Just do what you're supposed to, but whatever you change on one end, you got to change on the other. Okay? So we know that the torque is equal to RF sine theta. We know that in this case, the R here is going to be the radius of the pulley. And just like the last lab, we're going to use the biggest pulley, and that radius is listed for you in your lab sheet. The force is, of course, the force of tension of the string wrapped around the large pulley. And the angle in between, well, again, please set it up so that the, let's see here, yep, set it up so that the pulley here is tilted so that the string comes off tangent to the big pulley, right? Then if this is R, the string, the force of tension then, is tangent, which means the angle is going to be 90 degrees. The sine of 90 is 1, and therefore we can calculate the torque by taking the radius of the pulley times the force of tension. Right, again, read this, right? You got to clamp on the super pulley so that it's adjusted at an angle here, like in the picture, so that the thread comes off tangent and goes right through here. That way when it's going up and down, it won't, fly off the pulley. If you try to hook it this way and wrap it around the biggest pulley, you're going to have some issues, right? So if you want to use the biggest pulley, like in this picture, you got to tilt this. Should be set up that way now, but, So, question then becomes, okay, if this is how we calculate the torque, well, how are we going to find the force of tension? Well, just like last time, we do a quick force diagram of those hanging masses. Force of gravity down, force of tension up. Are they balanced? No, they can't be balanced. Why? Because it's accelerating. In what direction are these masses accelerating? Down. So therefore, the force of gravity has to be bigger than the force of tension. Don't fall into that common error that these forces are balanced. That would only be true if it was moving at a constant velocity or not moving at all, right? If it's accelerating, forces have to be unbalanced. There has to be a net force. Of course, we know that that net force will be equal to mass times acceleration, Newton's laws. Our force of tension is up, so positive. Our force of gravity is down, so negative. and our acceleration is down, so also negative. So if we write this out, getting rid of all of the vectors and turning it into a beautiful scalar equation, the force of tension minus the force of gravity equals negative ma. Again, up positive, down negative, down negative. Solve for the force of tension. F of g is, of course, mg. Factor out an m. Well, we know the mass, right? Or you will know. It tells you on the lab sheet what to hang on the end of the string. We know the localized gravitational field strength, of course, 9.8 newtons per kilogram. But what is the acceleration of the hanging masses? This, by the way, is a linear acceleration. Right? What is the acceleration of the hanging masses? Well, we don't know that, right? But we can find the angular acceleration of the pulley. Right? How? Or, the pulley, the rotary motion sensor, right? How? The same way we did in the last lab. Okay, you'll open up a Data Studio file, and it'll be a big graph of angular velocity versus time, the slope of which is the angular acceleration. Right? So we can experimentally measure the angular acceleration. How are we going to turn that into the linear acceleration of the masses? Well, again, as we did in the last lab, we have to remember that this string is going to be wrapped around this pulley and will move in such a way that it does not slip on the pulley. Since it does not slip on the pulley, what has to be true about the motion of the outside of the pulley and the motion of the string, hence the masses attached to the string? It's got to be the same motion. Right? If one is moving faster or slower than the other, there'll be slippage. So that means the acceleration of the masses, linear acceleration of the masses, has to be equal to the tangential acceleration of the pulley. Tangential because the force of tension is tangential, if you set up the lab equipment correctly. These are A's, not alphas. But we know how to calculate the tangential component of the linear acceleration of the outside of the pulley. It is simply alpha r. Alpha is the angular acceleration, the slope of the angular velocity time graph experimentally, times the radius of the pulley, again, given to you in the lab sheet. So, last lab, I had you calculate these things like one at a time. You calculated this, then you calculated this, then you calculated that. This time, though, I want to make the lab a little more straightforward with one big calculation. So we're going to plug this value into there, right, into that A. And then we're going to plug this F of t into the tension, or torque equation, sorry. And we'll get torque equals R times M times the quantity G minus alpha R. Be careful, this is an alpha. Everybody okay with that? Plugged this here, plugged this whole expression right there. Okay? So that's the torque. But remember, as we found in the last lab, Newton's second law says torque equals rotational inertia times the angular acceleration. Torque is I alpha. So that means we can calculate I by taking the torque and dividing by the angular acceleration. Well, we'll know the angular acceleration from the lab, the slope of the angular velocity time graph. And we know now an expression for the torque, so if we plug it in, we get one big old equation to allow us to calculate the experimental rotational inertia of the point masses, right, and the bar, for that matter. Now, note that the R's here, both R's are the same. They are the radius of the pulley in the lab sheet. M is the hanging mass. It's not the mass of the point masses, it's the hanging mass. Think about how we derived that, right? It came from an analysis here of the hanging masses. That's where the M came in. G is the gravitational field strength. Both alphas are the angular acceleration. So if we're careful and we do our algebra right, we can plug this all in and in one big old equation calculate the rotational inertia. And then we can change something, right? Either the masses of the point masses, right? Or where those point masses are. The distance from the axis of rotation, right, are two variables. So we're going to use this equation quite a bit. You with me there? If you need it, go back over the proof again. Again, I did put this on the lab sheet. Speaking of which, I want to talk about the lab sheet a little bit. Okay, so if we go back to the beginning here, you should have a lab sheet just like this, I hope. Here's our purpose. This tells you, how to find the program that runs the equipment, runs the rotational probe, and also rotational motion sensor, and also is just a big graph of angular velocity versus time. This one's talking about how to make sure the super pulley is angled right. Here's the radius of the biggest pulley, just like the last lab, 0.024 meters, a little less than 2.5 centimeters because you're in the groove, right? The mass hanger, don't forget the mass hanger is 5 grams, right? And hopefully it should be set up where you're getting positive rotations, but in other words, it's rotating counterclockwise, right, as the mass falls. If not, you have to wrap the string the other way. So we do have to take care of one little issue, though, which is that I want to figure out a math model that's about the 2 point masses. What's the rotational inertia of the 2 point masses? But more than that is rotating. Right? That rod that they're attached to is also rotating. Now, that rod doesn't have a ton of rotational inertia because it doesn't have a lot of mass. It's made out of aluminum, but it is enough that it would change the answer slightly. It would be a source of error. So we're going to do an extra part of the lab. Part 1 is just to figure out the rotational inertia of the rod by itself. Once we know that, we can subtract it from the rotational inertia when we actually have point masses on it, and that'll get rid of the part due to the rod and leave us with just the point masses. With me? So, in this part, you're going to take the masses off the rod, unscrew them, move them off to the side. You're going to place only 20 grams, 0.020 kilograms, on the mass hanger for a total hanging mass of 0.025 kilograms. You're then going to measure the angular acceleration 3 times, take an average, and use our big honkin' equation we just derived to calculate the rotational inertia of just the rod. Again, the m is the hanging mass, and the r is the radius of the pulley. Right? So you don't even need to know the mass of the rod at all for this part. You just need to know the hanging mass, which should be, if you put a 20 on there, not a 50. You put a 50 on there, it's going to fly, right? So we just need the 20. That's part 1. Once you know the rotational inertia of the rod, you can move on to the actual lab parts, right? Where we vary one of the parts and keep the other constant. So part 2 is rotational inertia versus total mass with constant distance from the axis of rotation. So you're going to put the 2 brass masses back with their, you're going to mass them first so we know how much mass they have, and there's a place to put that right here in the data table. Mass of both masses with screws. Okay? And then you're going to put those on the ends of the rod. Make them flush with the end of the rod. Okay? And then you're not going to move them. So you are going to measure so that we know the constant, the distance from the axis of rotation, but be careful here. Obviously we measure from the axis, which is right in the middle, right? But where do we measure to? Well, hopefully you're saying we need to measure to the center of mass of the point masses. Right? And it should be the same both ways, right? There should just be one number for that. That means right at the center of them, basically. Because you don't want to underestimate where they are or overestimate where they are and go to the ends, right? So go to the center of them, right? Measure that with the ruler, and boom, you've got the distance to the masses. Once you know that, you're going to place a 50-gram mass onto the mass hanger for a total of 55 grams or 0.055 kilograms, and you're going to leave that on there for the entire part 2 and 3. Okay? Remember, that's also the mass that is in the equation, right? So take the 20 off, put the 50 on. It's because the 20 it's not enough torque, right? We need more torque to make it move a little faster. So switch to a 50. All right? Now, as I said, if you change one of the masses, you have to change both to keep everything balanced so there's no vertical net torque, right, which could hurt the rotary motion sensor, and it's an expensive one, so be nice to it. So if you add some mass to one end, you have to add mass to the other end. The total mass that we're looking at then is the sum of the 2 brass masses with their screws, which you'll list in this column, plus masses that you'll add. Now you'll notice when I said added masses, right, the first one is 0 added mass because you're just going to do the 2 brass masses with the screws. That'll be the total mass too, right? Run 3 trials. Then it says 2 times a 50 because you're going to add a 50 to both sides. Ah, you with me? 150 on one, 150 on the other. And then you're going to add 100 to each side, 120 and 150 to each side. It's as much mass as we can fit underneath my screw. So that'll be all of our data points. Okay, we do have a 0, 0 here, but we'll also have one that has a total mass of just the brass masses and the screws, and then we'll start adding masses to that. Right? Don't move the masses. Leave them straight where they are. Once you get that, well, then you can come to the next table here. Here's the equations. Average angular acceleration, the rotational inertia of the system, which is just running this equation, where again the m is the hanging mass, which is now 0.055 kilograms, because you put a 50 on the end of the string, I hope. And the radius of the big pulley that you wrap the string around, still 0.024 meters. Calculate this out, that's the system. But I don't want to know the system. I want to know the rotational inertia of the point masses. So what do I have to do? Subtract off the rotational inertia of the rod. With me? That you found in part 1. So whatever you calculate here, you'll subtract off the rod, and that's what you'll get. And then we're just left with the point masses. Clever, isn't it? I didn't make it up, but it works. And you're going to do a graph and, and math models and all that kind of stuff. At one point, you're going to go onto the schedule doc and open up a Google Doc and put in a couple of things so we can gather everybody's info. Part 3, change the distance, keep the total mass constant. So this time you are going to just mass the 2 brass masses with their screws and record here as the constant total mass. So you have, one side, the other side, and the total. Okay? Then you're going to put them back on at equidistant positions. These are positions from the axis of rotation to the center of mass. Right? You're not going to add any more masses to those. You're just going to use the brass masses and the screws. What distances are you going to use? These distances. 7 centimeters from the axis. 10 centimeters, 13 centimeters, 16 centimeters, 18 centimeters, which ought to put them pretty much at the ends. Right? So you're going to start them close in and get them further apart. As before, if you move one mass to 7 centimeters away, you need to move the other mass 7 centimeters away so that you don't have any net torque vertically. And again, remember the distance is from the axis of rotation to the center of mass of the point masses. Be as precise as possible, otherwise you'll have error. That's where most of the error in this part of the lab is going to come from, is going to be, did you really put the masses the right distance away from the axis of rotation? 3 angular acceleration trials, and then a similar kind of process. Average angular acceleration, plug it into the equation to find the system inertia, subtract the inertia of the rod, and boom, there you go. You've got the rotational inertia of the point masses at different distances. Graph, this one's going to take a linearize, and it's a similar kind of process. Again, there's another part where you have to go in, make sure you're opening the correct Google Doc. It's part 3, right? And entering in your information there, okay, along the way, and making math models and all that good stuff. And then in the post lab, I am going to show you how to take the 2 parts of the lab and shove them together into one math model for the rotational inertia of point masses.